I have 8 years of experience in academics. My research area is parallel computing and computer graphics. And also I have been a consultant and a corporate trainer for some industries. So I'm excited to present this new graphics API to you. The topic is future of open source graphics. The rough agenda is like this. We start with the graphics APIs and we move towards the new API called as Vulkan. And what is the industry and platform support for it, certain design goals, discussions, and code walkthrough. And since it's a future, let me predict something. So graphics APIs, it started all around 1980s when we had a requirement of developing a software that could function with a wide range of graphics hardwares. It was a real challenge. The software developers wrote a custom interfaces and the drivers for each piece of hardware. This was expensive and resulted in multiplication of effort. By the early 1990s, the Silicon Graphics, SGI, was a leader in 3D graphics for workstations. Their Iris GL was considered the state of the art and became the de facto industry standard. Later it was fixed, and due to certain problems like immediate mode rendering, it was difficult and it was considered as outdated. Then the competitors of SGI like Sun Microsystems, Hewlett-Packard, and IBM, they tried combining the features of Iris and certain features from SGI, but it was a failure. So it was an initial attempt towards building the OpenGL. In 1992, the SGI led the creation of the OpenGL Architectural Review Board, OpenGL ARB we call it as. It is a group of companies. It maintained and expanded the OpenGL specification for the future. An interesting part appeared in 1993. It's called as Mesa implementation, which is the one we often use for Linux, where we are going to have packages for OpenGL that can be worked in open source environment. And there was an attempt in 94 to add certain features, the Scene Graph API, and again it was not turned into any product. In 95, we have Direct 3D from Microsoft was introduced based on the developments that has happened till 1994. Then 2004 came the OpenGL 2.0. So with GLSL capability. So GLSL means graphics language shading language. So here you would be knowing that the graphics works based on the GPUs, the graphics processing units. So initially the approach was a fixed pipeline. All the details were provided by the driver vendors, graphics driver vendors, and you are going to have a set of program which was having a static way of coding, and you are able to access the graphics APIs through the functionality which was provided by the drivers. So how we can exploit? Later an idea came into picture how we can exploit the functionality of GPU itself such that we can get a performance gain. So they tried accessing the core components of GPU, the vertex shaders and the fragment shaders. So there the concept of GLSL was originated. Then in 2006, OpenGL architecture review board, it was handed over to an open consortium group called as Kronos group, so which is now also taking care all the OpenGL related facts. In 2008, OpenGL 3.0, it introduced a deprecation mechanism to simplify the future revisions of the API. Certain features were deprecated, but it was not completely disabled. So you can have a forward compatible context. So you can request for that. For example, like the windowing system. So by requesting a full context, so you can access the old features in OpenGL 3.0. So some of the deprecated features include all the fixed function vertex and the fragment processing, due to which it was hindering the performance. Then there was something called as direct mode rendering. So those who have worked with OpenGL, you should be knowing we had the calls GL begin and GL end. So which it is called as the direct mode rendering. Then all the points or the vertices, they were fed into a file called as display file or the display list. So which is a classical one for the even the BIOS level graphics. So display list was also deprecated. Then indexed color rendering targets. So and also the OpenGL shading language versions 1.1 and 1.2, they were considered as deprecated. So in 2012, it is OpenGL 4.3, where you had a lot of hardware support from the vendors like NVIDIA, ATI, that's AMD, then the Intel HD graphics hardwares. They all came up with certain features. The important one among them was the compute shaders. So all the mathematical calculations related to certain graphics were provided in terms of compute shaders. So then, hand in hand, OpenGL ES for embedded systems 3.0 came into existence. So it targeted millions of devices, handheld devices, in which you can also nowadays do the programming with respect to the iOS or Android, which uses the context of OpenGL ES, and they have built upon something called as iOS people, they came up with the EGL. So then we also have the WebGL as one of the latest standards, which works on the browser. The graphics was moved from a command-based prompt towards the browsers. And as the name says, OpenGL, it was an open source initially. So later there was certain licensing imposed on the OpenGL. But all the graphics vendors, the gaming industry and the entertainment industry, as well as the GPU vendors, so they are providing the OpenGL versions. So in 2014, it was OpenGL 4.5. It was having a new concept called as direct state access. The OpenGL was considered as the state machine. All the happenings in the OpenGL, it was binded to a context, which was a static one. So you're not supposed to change that. Once all the values and the variables are binded to that context, so it is going to run that context continuously in a loop. So then you are supposed to get the access or the display was happening. But it was diverted by using the direct state access. So there were object accessors that enable the state to be queried and modified without binding the objects to the context. There was no binding of the objects to the context. So it gave the application and the middleware efficiency and the flexibility. And there were flush control, which was, we were using the GL flush. So application can control the flushing of pending commands before the context switching. So enabling the high performance in the multi-threaded applications. Then there was a robustness. It provided a secure platform for applications such as WebGL browsers, and it was preventing a GPU reset affecting any other running applications. So there it provided the OpenGL ES 3.1 and also the shader compatibility. So this enabled the easy development and execution of the latest OpenGL ES applications on the desktop systems. In Feb 2016, just 1 month before, the Vulkan API was released. It was long awaited by all the graphics programmers and the graphics industry. So why a new 3D API was required when you had several other APIs? So as we saw in the history of OpenGL, everything has not stood the test of time. As we discussed, the OpenGL API is a state machine, and it was bound to a on-screen context. And the main problem was OpenGL was hiding whatever is happening inside the GPU, because that hiding is also enabled by the drivers. So it was making sense in 1992 because people were not interested towards working towards the hardware internals. The software programmers didn't like to work towards hardware internals. But now the graphics has reached such a level that unless you know the system internals, you will not be able to do the graphics programming. So what is this Vulkan API? It's a new 3D rendering and compute API from Kronos. It is a cross-industry group that maintains the OpenGL. This has been redesigned from the ground up, and it's not OpenGL++. And it has been designed for the modern GPUs and the softwares. And it will run on currently shipping hardware. The goals of Vulkan API is a clean modern architecture. And the years, maybe 1 decade, the people are working on multi-threaded applications. Again, the concept of multi-threading, the parallelism is exploited in a great depth in the gaming programming. So it is, the concept was originated from the game programming, and it has been extended towards the GPU also, the general purpose programming in the using the graphics processing units. And this API has reduced the CPU overhead, and it has full support towards all the different devices, multiple devices. And there is a predictable performance because it is not going to hide more details in the driver. So what is the thing that has provided by the Vulkan? So it has revealed the driver code, which was not accessible, which was considered as closed source before. So now it is not all the code is revealed, but a part of that is revealed which can be utilized for further graphics programming. what is different with respect to the Vulkan? So initially it was constructed as a low-level C API, which also extends its support towards the object orientation, and it has no global state. And the WSI extension for Vulkan is provided. WSI means Windows System Integration. So it is a mechanism by which the images are rendered and it appears on a screen. And this Vulkan WSI has a notion of a platform and the integration. So it is going to abstract you from the particular operating system or windowing system your app is running on. So that is a very good feature provided by the Vulkan. And what else? It also provides the texture formats, memory management. Again, all these are separate concepts. It can be considered as a new area of computing, which involves the operating systems and the system internals. And syncing, the synchronization, different kinds of synchronizations are defined in this. They are all client control. It is in the same way as we see nowadays the servers. There are some web servers which are developed by the JavaScript. The client is going to control the server artifacts. So that kind of independence is given to the client, and certain things are hidden such that the client is not going to make the GPU or the rendering crashed, because when you are accessing the driver related facts, so it may collapse the GPU if you don't know exactly what has to be done, and there is no explicit error checking done by the Vulkan drivers. So for this purpose, it has a code base which provides the basic functionality, and all these exception handling mechanisms and several different actions, they are provided as the layers, different layers. So you can access those layers separately. The toolkits and the tools chains are provided for that. So why we should care about this Vulkan? So it has become an open source. There is GL slang, which is a specification. All the OpenGL programs and the Vulkan programs, they bind to this GLSL, the GL slang specification. So if consider we have a command, GL slang command, a common command for all the platforms. You pass the shaders to this, it will compile and give you the results. If it compiles properly, so then it will be compiled by the Vulkan and all other APIs. So that kind of standard is this GLSL, and they also come up with a new standard called as SPIR. So this is GL slang is an official reference compiler for the front end for OpenGL ES as well as the OpenGL shading languages. It has strict interpretation of the specification for these languages, and again it's an open and free for anyone to use. And all the communities, they have to maintain a consistency between the reference compiler and the corresponding shading language specifications. So there is open source drivers. It has been released few days before. Intel has released the Vulkan drivers for Intel graphics devices, and also NVIDIA also come up with drivers that support the Vulkan. It was AMD has built an open source for their Vulkan driver, and it is already in the way. And by using all these, the community can write more. And one more important point is it is easier to package and distribute the deployment related information, and it is easier to integrate into the toolkits. And also it will bring most of the applications towards the open platforms. Just 3 days before, maybe from 14th to 16th, there was a GDC conference 2016, the Game Developers Conference. So in which they have revealed several details about this Vulkan. So there they have a lot of gaming industries, they already have built a prototype for this and they have demonstrated. It doesn't only work for 3D, it also works for 2D also. So how it can be customized to work with the 2D. So that means the gaming people who are working for DirectX and all other graphics implementations, they are moving towards or focusing towards the Vulkan. So you can see the certain videos already released in the YouTube showing the performance benefits if you use the Vulkan. So, and other challenge is that it is an open source. The learning curve is steep. So it provides an opportunity for the education. You can introduce certain courses related to this Vulkan in the future, because it is going to, its object model is going to match the hardware better. So it's a practical demonstration of all your object-oriented programming, the graphics programming, the operating system internals, the advanced system architecture, all these subjects. So what we have now, we have specifications, we have man pages built, the GLSL to SPARE 4.5 compiler, and there is a very basic SDK provided which has certain loaders and the layers. And conformance test is on the way, it's not fully completed. And all the resources are open source. So these are the conformant drivers, the imagination, the Intel, NVIDIA, Qualcomm, ARM, Samsung, and AMD. And there is a third-party tool. It's called as LUNAR G SDK. So you can register to that, and you can get the independent hardware vendor, and you can get that SDK. There are again some other independent hardware vendors and software vendors. So there is one very big game built, the Talos principle. So it has beta Vulkan support. And what are the different platforms supported? It has all the leading platforms. Again, it's happy to see that Red Hat is also contributing to this. Android, Windows 10, and Ubuntu is also there. So that means Vulkan is a cross-platform. Any OpenGL ES 3.1 or up to 4 point any version GPU, so it can be supported by in the Vulkan. So GitHub repository is available. So they have already taken the pain, a lot of pain from 1 year to do the, they have taken a lot of commits and pull requests were there, and errors have been fixed now. So what are the design goals of Vulkan? So this is the official logo of Vulkan, which has a teapot model, which is the basic model of computer graphics, and also all the leading bunny or dragon. So these are all considered as standards for standard benchmarks. So we will see certain design goals. So it is an explicit API. So all the state definitions, so they are going to be provided in a different manner. So state definition, for example, if you want to render a circle or if you want to render a triangle, so you are going to create the API objects for them. So all these things are done by creating the pipelines. There are pipeline objects, there are layer objects, there are memory objects in this, and there is no driver magic. Everything is in your hand, and the scheduling is also in your hand. How the CPU and GPU can work in a collaborated manner, the synchronization between the CPU and GPU. So that's an important discussion that has happened in the Vulkan team. And it is portable due to several reasons, like the fixed function blending or the vertex fetch. All those things are static ones, whereas when you have a programmable pipeline, so it is more portable. And also there is a facility to port from the fixed pipeline towards a programmable pipeline. So programmable pipeline means, so you're going to change the way the GPU is working, the default way of GPU for handling the graphics. So that is called as a programmable pipeline. So this is the an SDK provided by LUNAR G. So you can register to this, and there are 3 versions: Windows, Linux, and the Android versions available. So you can test. So I recommend this particular API because it will be the future of computer graphics. So there are 2 ways to explore this. As an enthusiasm, you can just download this API and test it. If you are serious about moving towards making a career in the computer graphics, so you can take the code, and there are basic examples provided in the GitHub. So work with that. It's not easy. It will take at least a month to understand the whole code base. So if you are serious enough, there is a lot of demand in all the different companies for even in the driver level. You may be knowing that the driver programmers are hunted now. They want more driver programmers. So that's one way. Another way is if you want to have an R&D, so it's a very good area which explores a lot of concepts, and you can get a concrete thesis out of this. So these are the 2 ways in which you can explore the Vulkan API. So now let me have a code walkthrough. The overall picture is that your initialization mostly looks like VK create instance, VK for Vulkan create instance. So this is in sync with the APIs like OpenGL, which was creating the instances. And you can also first, once you create the instance, then you have to query for the devices present over there. Devices in the GPU context, the devices means the GPU, or it may be FPGA also. So VK enumerate physical devices will give you list out all the devices present over there. So then from the available devices, you create a new device by calling in there is a call called as VK create device. So this is how we are going to initialize. Once you initialize, you will be working with the either you are going to create a model or you are going to manipulate an image. So if you want to create a model, use the buffers. Different buffers already in OpenGL, different buffers are present. So now you have a VK device, we can start creating pretty much every other resource type by using this. For example, VK image and VK buffer. So it provides access towards the image and the buffer objects. So I'm encapsulating all the complicated calls and just presenting the gist of that. So those buffers and the images can't be used immediately after the creation, as no memory has been allocated for them. Now, this is the step for you. All the memory management stuff can be done here. So the available memory is exposed to the applications by the VK get physical device memory properties. A call is there. So here it is going to query the heap of the given size. You can specify the size over there in the API. And one or more types, what kind of types and what are the properties, you can specify that. Each memory types comes from the heap, from one heap. So a typical example is that for a discrete GPU on a PC would be 2 heaps, one for system RAM and one for GPU RAM. So once you have the right memory type and the size and there is something called as alignment. You can start binding it. You can bind it by using the calls vk bind buffer memory or vk bind image memory. This binding is immutable, and it must happen before you start using the buffer or the image. Next step is whatever the work is happening, it is explicitly recorded and submitted from a vk command buffer. So now the sequence of commands. So it may be a new concept, or some people may know about that. So the sequence of commands can be pushed into a command buffer, and it can be executed by putting that into the loop. So command buffers are submitted to a queue called as a vk queue. So all the commands reside inside that queue. So next is that you can submit that queue. Like this, there are several command buffers at once. They will be pushed to the queue, and they will be executed in turn. You may have exposure towards the graphics pipeline, the older graphics pipeline, then the programmable graphics pipeline. Now in the Vulkan, the pipeline itself is a kind of object. You can create multiple pipelines. So it makes a lot of state, but allows specific parts of the fixed function pipeline to be set dynamically. This is how you are accessing the static code dynamically. So things like the viewport, you would have heard about the viewports in the graphics. The viewport, the stencil masks, the references, the blending constraints, all these things are present in the pipeline objects. A full list as ever is provided in the specification. When you call this vk create graphics pipelines, so it is going to return the vk pipeline object. You choose which states will be dynamic and what other values are taken from. The creation information is taken from this vk pipeline. So in Vulkan, the base binding unit is a descriptor. So we always talk about the descriptor queue, descriptor states of the descriptor. What do you mean by a descriptor? It is an opaque representation that stores one bind. It will have one particular bind. It could be an image, it could be a sampler, it could be a uniform or a constant buffer with respect to the graphics terminologies. And it could be arrayed also. So you can have the array of images that can be of different sizes, as long as they are all 2D floating point images. Then Vulkan has the vk event, vk semaphore, and vk fence, so which can be used to efficient CPU to GPU and GPU to GPU synchronization. So it is called as multi-GPU and host to device synchronization. So CPU to GPU is host to device, and GPU to GPU is device to device synchronization. And there are image barriers. They have one additional property. Image exists in the states called as image layouts. Then we have the render pass. It is the Vulkan's way of more explicitly denoting how your rendering happens. Rather than letting you render into the sample images, and how the frame is structured by using the rendering on a given target. It happens, and what are the dependencies that are between the different passes. Again, the passes are considered, passes in the GPU, they are considered as the objects. So to The last one is the back buffers and the presentation. So it has, Vulkan exposes the native Windows system integration via the extensions. So you have to request, you have to start with the VK surface KHR. So it is through which you can access all the native presentation layers. All these are done by the normal VK image handles. But you don't control their creation memory binding. So this is all of these are done to you. So that means we have to create an VK image view for each one, and it has to be presented. So that's the whole rendering pipeline. Even the presentation is considered as the sequence of objects, and it is rendered in particular manner. So that's the development path. An Vulkan application is there. There are loaders, there are validation layers, different kinds of debugging layer, and the other layers are present. And finally, it will be produced as an installable client driver. The concept of the message is that the asynchronous nature of GPU. It is the key design principle in the Vulkan. So you have an application, you have the command buffers, you have the command buffers are divided into even and odd, which will be sent into the GPU. There are different queue operations. You can insert into the queue, delete from the queue. So finally, the whole thing is considered as a queue object, and it will be finally you are going to get a driver out of it. So there are several vendors. Whole industry is working together. The GPU and the system on chip vendors, the game and the middleware developers, Unity and several other people. The platform owners are there, the content providers are there. All are working together. And the prediction is that we have the proprietary driverless car. So maybe in the future we will be having the driverless graphics. The most of the features are provided to you in your hand. What level of performance optimization you want, so you can achieve by yourself. Thank you. Any questions?
Hello. I have a ground zero level knowledge of graphics API, but in one of your slides you spoke about there's a compatibility break if you are going to use OpenGL along with Vulkan. So in that sense, my question to you is, consider that you have an application which uses this new framework, but some of its modules are still trying to use OpenGL. So how do you take care of that?
Yeah, there is a compatibility between OpenGL as well as the Vulkan. So already some calls from the OpenGL, so the code can be mixed together. So that kind of functionality is provided already.
No, so your slide talks about that there is a break, compatibility break in OpenGL versus Vulkan. So you mean to say that there is no break in compatibility?
So if you see the naive OpenGL, you'll be having the state validation or the pre-compilation. In the naive OpenGL it is not there, whereas in the Vulkan it is there. So there are certain differences between the OpenGL and Vulkan, but also there are certain commonalities, because Vulkan was designed by taking the inputs from the OpenGL itself. It is just we can say that it's a new version. OpenGL 4.5, it was supposed to be released, but they have renamed it as, we can call it as, they have renamed, maybe due to the business thing, they have renamed it as Vulkan. So that there are applications which has been demonstrated which involves both the OpenGL as well as the Vulkan. So in that case, you have to be very careful how it is querying, how you are going to query the OpenGL as well as the Vulkan. The same thing happened in the older versions of OpenGL when there was a fixed pipeline and there was a variable pipeline. So you are having you can change the mode and you can access the older calls. but it comes with a performance factor. It will be less outperforming. So, but for example, the retro named one game, it has been already ported. So what they are doing is, if there is an OpenGL version, they took around 1 month to convert it into a Vulkan. That time is reduced. If you want to convert it into a fully Vulkan one, because now you don't have any tutorials, very less tutorials and very less books about this. There is no book only. We are expecting one developer guide coming up. So once there is a lot of materials available, maybe in a week, an application, a game can be converted into Vulkan. So that much similarity is there between the OpenGL, the concepts of the OpenGL and the Vulkan. The API calls are changing.
Okay. Okay.
Is, first of all, why would graphics library would have CPU overheads, and which sort of those are reduced in Vulkan that used to be there in the OpenGL?
Yeah, before we send the command queue to the GPU, there are a lot of processing that happens, because given, for example, a triangle rendering, 3 vertices are there with interpolation color model. So it has to be prepared, lot of details has to be prepared in the host. The first step is to query the host memory itself, which will be working on the CPU threads. So then you are going to build it into a command buffer which is accessible to the device, and there is a pass time from the host to device. That means a lot of pre-processing happens, even in the graphics, a lot of pre-processing happens in the CPU. But those are not the graphics kinds of computations which is very tedious, but there are involvement of ALU, of course, and also the memory as well as the CPU threads. So then it is sent to the GPU. There it's again it's a new world. Again it will be sent back. Once it is processed, the certain results are sent back to the CPU as well as it is rendered on screen.
Yeah, so now that I understand that part, then how is it going to be different in Vulkan? Because from your explanation, it's going to be same way now as well, right? Because that has to be pre-processed and before sending to the GPU.
Yeah, as you can see here, the multi-threaded work creation and the submission, it was not there in the NavGL, but it is supported now in the Vulkan. So that's the main difference which we can see.
Thank you for that.
What Apple uses and how does it compare in terms of state-of-the-art? Apple Corporation. Do you know anything about it?
I didn't got your question.
The Apple Macintosh or iPhone. Can you tell us a little bit about what they use and how it compares?
Yeah, there are again the iOS people are working on this because it provides the Android bindings. iOS they can access by the embedded C. By using that they can program it. I think already I have not explored that, but already Apple would have been working on this to provide certain functionality, because Android applications are running already. So maybe iOS, they have not published anything because it is just 1 month has happened. This API has been released. Maybe they are working now.
Excuse me. Hi. The slides you mentioned that Vulkan has a different object model that is more suitable to the hardware. How, what the object models you are talking about and how is it? Can you elaborate on that?
Just for an example, you have in the presentation layer. So if you want to create a native window surface, initially that is platform specific APIs. Then you want to create a surface, Vulkan surface, it is considered as an object. So if you want to query the device, it's again an object. The pipeline is an object. The passes in the Vulkan, that is in the GPU, it's also an object. So they have an object model such that they want to come out of the state-based API. If you know the basic OpenGL, it was purely state-based. The rendering was not happening till all the states are initialized properly and it is rendered at once. To come out of that particular property, now they have built this object model, which was existing in the OpenGL and CUDA kind of APIs already. So it has been taken and added to the Vulkan.
Okay, thank you.
There will be two system heaps which will be used by the Vulkan API. How the embedded systems will be getting that much heap memory when they have a constraint on the memory?
The whole memory is, you can query the memory as in the memory management functions. There are memory management functions. For example, VK get physical device memory properties. So by using, it reports one or memory heaps of the given sizes. So it may be one or it is more. So through that, if the system has that kind of power, so then it can query. There are certain calls in the Vulkan which is reserved for future. In the future also you may have certain concepts like multiple heaps, and there is a possibility of creating n number of heaps in the hardware support. So they have reserved certain calls for the future. So now also you can query if, for example, if the system has one or more memory types, so with the given properties, whatever the given properties you have fed to that call, so each memory type comes up from one heap. Okay, it's a typical example for a discrete GPU on a PC. It would be having two heaps, one for system RAM. So that's a common thing in the BIOS graphics programming, and another one is for the GPU RAM. So they are coming together, and you are going to construct a heap model. So all these are object models which are in the Vulkan API. So finally, it's a software abstraction for the actual memory model. It's a system RAM as well as the GPU. Two heaps are considered like that. So maybe in the future you may have more devices for which you may require more heaps.
Okay.
Thank you very much.